Hello friends, this video is brought to you by www.moeteaching.com.
Polynomials. In this chapter, we will extend our study to geometrical meaning of the zeros of a polynomial, relationship between zeros and coefficients of polynomial, and division algorithm for polynomials. We have studied polynomials in class 9th, chapter 2. You can go through the videos and revise it. Here we shall start with revising some basics that would be required for the further study about polynomials. We start by revising the degree of polynomial px. If px is a polynomial in x, say px equal to 4x plus 2. Then the highest power of x in px is called the degree of polynomial. In this case, the highest power of x is 1. So, degree of this polynomial is 1. A polynomial of degree 1 is called a linear polynomial. More generally, any linear polynomial in variable x with real coefficients is of the form px equal to ax plus b, where a and b are real numbers and a cannot be 0. Now consider another polynomial, say p of y is a polynomial in variable y equal to 2y square minus 3. Since highest power of the variable in this polynomial is 2, so the degree of this polynomial is 2. A polynomial of degree 2 is called quadratic polynomial. General form of a quadratic polynomial is ax square plus bx plus c, where a, b and c are real numbers and a cannot take the value 0. Likewise, we define cubic polynomial as is a polynomial of degree 3. For example, say gy is a polynomial in variable y, then 2y cube plus 5y square plus 7y minus 8 is a polynomial with highest power 3, so it is a cubic polynomial. General form of a cubic polynomial with variable x is p of x equal to ax cube plus bx square plus cx plus d, where a, b, c, d are real numbers and a cannot take the value 0. A biquadratic polynomial is a polynomial of degree 4. H of u is a polynomial in variable u and highest power of u is 4, so it is a biquadratic polynomial. And the most general form of biquadratic polynomial with real coefficients in variable x would be p of x equal to ax power 4 plus bx cube plus cx square plus dx plus e, where a, b, c, d and e are real numbers but a cannot take the value 0. So now we come to the general form of a polynomial of degree n, where n is a positive integer. It would be p of x equal to an x power n plus a n minus 1 x power n minus 1 and so on till we get a1x plus a constant a0. Here an minus 1 and so on a1 and a0 are real numbers and an cannot take the value 0. Let us now recall value of polynomial. Say we have a polynomial in variable x, fx equal to 2x square minus 3x minus 2, then value of this polynomial at x equal to 1 would be, substituting x equal to 1 in the polynomial, we get answer as 2 minus 3 minus 2, which is equal to minus 3. So minus 3 is the value of fx at x equal to 1. Note here, fx is a quadratic polynomial. Now suppose we find the value of fx at x equal to 2. Then f of 2 will be 2 into 2 square minus 3 into 2 minus 2. On solving further, we get 8 minus 8 equal to 0. So value of fx at x equal to 2 is 0, and we can say that 2 is the 0 of the polynomial fx. Now we are in a position to define 0 of a polynomial. A real number a is a 0 of the polynomial fx if f of a equal to 0, like in this example. 2 is the 0 of polynomial fx equal to 2x square minus 3x minus 2. Also recall that polynomial of degree 2 will have 2 zeros. In general, polynomial of degree n has exactly n zeros. Consider a linear polynomial, say p of x equal to 2x plus 3. If some real number k is 0 of this polynomial, then p of k should be 0. This implies that 2k plus 3 should be equal to 0. Let us solve this. We get k equal to minus 3 by 2. So we have found out 0 of the polynomial px. Let us do the same thing for general form of linear polynomial, which is ax plus b. Let k be the 0 of this polynomial, then p of k should be equal to 0. ak plus b should be equal to 0. K should be equal to minus b by a. In other words, if we have a linear polynomial, then its 0 is minus the constant term whole divided by coefficient of x. So we have seen that 0 of linear polynomial is related to its coefficients. Let us see if the zeros of quadratic polynomial are also related to its coefficients. Let us take a quadratic polynomial fx equal to 6x square minus x minus 2. To find the zeros of this polynomial, we know the method of splitting the middle term. Let us recall, we multiply a with c and get 12, then prime factorize and arrange these in such a manner so that we get b. For instance, here we can arrange 2 2s are 4 and 3 in such a manner to get minus 1 by taking minus 4 plus 3, and then our polynomial becomes 6x square minus 4x plus 3x minus 2. Take two terms at a time. Taking out 2x common gives us 3x minus 2 plus 1 common gives us 3x minus 2. So we have 2x plus 1 and 3x minus 2 are the roots of the polynomial, and the zeros will be, by equating 2x plus 1 equal to 0, we get x equal to minus 1 by 2, and the other 0 will be, by equating 3x minus 2 equal to 0, x equal to 2 by 3 is another 0 of this polynomial. Let us give names to these zeros of polynomial fx. Say alpha is one of the zeros and beta is the other zero of the polynomial fx. Then sum of the zeros of the polynomial, that is alpha plus beta, will come out to be minus of minus 1 by 6, which is equal to minus the coefficient of x whole divided by coefficient of x square. If we take the general form ax square plus bx plus c of the quadratic polynomial, then it is same as saying that sum of the roots or sum of the zeros of the polynomial ax square plus bx plus c are minus b by a. We shall use this result as a formula. Similarly, we can find the product of the zeros of polynomial alpha into beta equal to minus 1 by 2 into 2 by 3 for the given example, which is equal to minus 1 by 3, or we can write it as minus 2 by 6, and then reach the result that product of the zeros of a polynomial, that is a quadratic polynomial, is constant term by coefficient of x square, and from the general form ax square plus bx plus c of the quadratic polynomial, the formula is c by a. We sum up by saying that if fx is a quadratic polynomial and alpha and beta are the zeros or the roots of this polynomial, then sum of the roots is equal to minus b by a, and product of the roots is c by a. we shall use this as formula. And again we have seen that zeros of the polynomial are closely connected to its coefficients. Similarly, if fx is a cubic polynomial and say alpha, beta and gamma are the zeros of the cubic polynomial, then sum of the zeros, that is alpha plus beta plus gamma, is equal to minus the coefficient of x square by coefficient of x cube, that is equal to minus b by a. Sum of the product of zeros taken two at a time, that is alpha into beta plus beta into gamma plus gamma into alpha, is equal to coefficient of x by coefficient of x cube, that is equal to c by a. And the product of zeros will be alpha into beta into gamma equal to minus the constant term by coefficient of x cube, that is minus d by a. There is an important result for a quadratic polynomial. Say if we have alpha and beta as the zeros of the polynomial, then we can find the polynomial fx by substituting in the following formula. F of x equal to some constant k times in bracket x square minus sum of the zeros into x plus product of the zeros. For example, if we are given that sum of the zeros of a polynomial is equal to 1 by 4 and their product is minus 1, then we can find the polynomial as fx equal to k times x square minus sum of the roots, that is alpha plus beta, which is 1 by 4 times x, plus product of the zeros, which is minus 1. So the polynomial will be x square minus 1 by 4 x minus 1. The graph of a polynomial fx is the collection of all points xy where y is equal to f of x. That means we will form the equation y is equal to ax plus b, and corresponding to each x we can find the value of y. In class 9th, we have studied that graph of y is equal to ax plus b is a straight line. That is why we call fx equal to ax plus b a linear polynomial. We will see that the line represented by y is equal to ax plus b crosses x-axis at exactly one point, namely minus b by a 0. And we know that minus b by a is the 0 of the polynomial ax plus b. Let us take an example and check out. Say fx equal to 2x minus 5. For the graph, we will write y equal to 2x minus 5. Now let us take certain values of x and find the values of y. If we take x equal to 1, value of y will be 2 into 1 minus 5, that is minus 3. If we take x equal to 4, value of y will be 2 into 4, 8 minus 5, that is 3. So we have the coordinates 1 minus 3 and 4, 3. Now since 2 points determine a straight line, so only 2 points are needed to be plotted to draw the linear polynomial. We plot the point 1 minus 3 and 4, 3 on the graph. Now if we plot the point where fx equal to 2x minus 5 intersects the x-axis, the coordinates are 2.5 and 0. And we also notice that 0 of the polynomial 2x minus 5 is minus b by a, which is minus of minus 5 by 2, which is equal to 5 by 2, which is equal to 2.5. Thus we come to the conclusion that 0 of the polynomial 2x minus 5 is the x-coordinate of the point where the graph of fx equal to 2x minus 5 intersects the x-axis. Hence we repeat, 0 of the polynomial is the x-coordinate of the point where the graph of fx intersects the x-axis.